All right, welcome everybody. Today's going to be lecture 15, and just for posterity, we're almost a full hour late starting today, so we might need to run a little bit overtime. But that's because we just watched the landing of the Intuitive Machines Nova C Odysseus lander on February 22nd, 2024. So if I refer back to this recording like years from now, that today was the day that happened. So that's fantastic. Really appreciate that you all took the time out to watch that, and I know it's going to screw up our lecture schedule, but I think it's important that we see things like that in real time. To refer back to our course map, I'm going to open that up in a second here. Let's see, course map. We're actually starting a new unit today. It's going to be, this is the start of the content for homework 3, and I'm going to go ahead and share my screen. There we are. Okay, so here is our course map when it loads. At least it hasn't loaded on my screen just yet. And so this is to illustrate kind of the entire class in one diagram. And so we start off with orbital mechanics, and we had quite a few lectures on orbital mechanics. And then we talk about the mathematics that lies kind of at the base of all things, and that's our estimation theory. And so that gives us the foundation that we need for the rest of the class. And we're approaching the halfway point of the class, and we haven't gotten to the cool stuff yet. So I think what we're going to start to see is that the units are going to start to speed up. The pace is going to start to speed up a little bit, but we're going to be building on previous concepts. So whereas before we spent a long time talking about things like covariance and expected value and the state of the vehicle and being able to propagate that state, those are going to start to be things that we take for granted moving forward. And so today marks the start of the magenta lines, which is triangulation and trilateration. I originally had that written down as radiometric navigation, but I feel like this is a little bit catchier. And so this is going to be using measurements taken from the ground to navigate things in space, or using measurements of things from space to navigate people on the ground. So that would be, for example, the GPS problem, right? So we'll be talking about GPS in the next couple of days. So at one point, I had this unit written as space to ground and ground to space navigation, which I think is also a cool way of talking about it. But I think triangulation and trilateration, those are the two math problems at hand. One of those is estimating the position of an observer using 3 or more distance measurements, that's trilateration. And the other is using trying to estimate the position of an observer using 3 or more angular measurements, and that's triangulation. So we'll talk about those mostly next class, and today is largely going to be introductions to that kind of concept. But so yeah, this is going to be ground-based or space-to-ground navigation. And we're only going to have about 2 or 3 lectures on that topic. And then we'll cover inertial navigation, which we only have 1 lecture on that topic. And that's going to be a nice natural stopping point for spring break. And when we come back, it's going to be pretty much all cameras and flight computers for the rest of the class. That's largely how it's going to break down. So why don't we get started on, let's see here, lecture 15, radiometric navigation. There we are. So start on with my pen here. So radiometric navigation. Or here's the question: how do we actually use those big old radar antennae? That's how you spell radar. So you might have seen, those big antennae that look kind of like this, and then like that, and that. And then there's like a thing, and it comes out there, and there's like a little crosshatch and what have you. That's my best ground station art. I think it passes. How do we actually use these things? All right, so we have these all over the Earth. We have Earth-based navigation or Earth-based observation stations that we can use to navigate spacecraft. And we also have a whole constellation of GPS satellites that we can use to navigate things on the ground. We're going to be talking about both of those in this unit, which is called radiometric navigation. So broadly speaking, if we have enough distance measurements. So if you know the distance from one ground station to the spacecraft, and then you know the distance from the next ground station to the spacecraft, and then you know the distance from the next ground station to the spacecraft, and so on and so on and so forth, that gives us enough information to solve what's called a trilateration problem. So this is called trilateration. One of my pet peeves is people who use the word triangulation when they mean trilateration. Those are different things. Another is if we have enough line of sight measurements. So you've got one observer measures the apparent direction to a spacecraft, and then a different observer measures the apparent direction to the spacecraft at the same time. If we have that information, that is called triangulation. One of them uses sides, like trilateral. The other uses angles, a triangle. Right? And so I'll also mention that the Deep Space Network, and this is all good, these acronyms are going to make sense pretty soon. The Deep Space Network gives us what's called R3B, which is range rate, and bearing measurements. That's what we can get when we're trying to track a spacecraft that's in deep space. And so this is just kind of an introduction. So we've got the trilateration problem, the triangulation problem. We're going to be talking about the Deep Space Network, and we're going to be talking about GPS. And that's going to be the next 2 lectures. So we'll start by discussing what radiometric navigation is. So this is going to be a lot of writing and not as much math today. And then most of the math is going to be in the next lecture, lecture 16. So radiometric navigation systems use the principles of light propagation to infer or to estimate, I'm going to use the word infer, information about spacecraft state. These systems use radio waves. So first question for anybody that's feeling brave and wants to pipe up, why is it that we specifically focus on the radio frequency part of the electromagnetic spectrum when we're doing space to Earth or Earth to space communications or navigation? Why not visible light or lasers or some other portion of the electromagnetic spectrum?
Not much gets in the way of it. Like
Okay.
it penetrates well through light and a lot of other things.
Ah, I like that. Very good. Very good. So the Earth's atmosphere, I saw a diagram one time that shows the whole electromagnetic spectrum. I probably pull that up. It's the whole electromagnetic spectrum and then what parts the Earth's atmosphere lets through. And it lets through visible light, but like kinda. It doesn't always do the best job at letting through visible light because we have a little bit of atmospheric effect going on. It's really good at letting through radio waves. And then it's awful, and thank goodness, about letting through like ultraviolet radiation, the stuff that gives you skin cancer, right? So our atmosphere is actually pretty good at blocking the really nasty radiation that kills people. Otherwise, we wouldn't be here. But it is pretty bad, and this is good for us. It's pretty bad at blocking radio waves. So radio waves tend to play nicely with our atmosphere, and I say that with an asterisk because our atmosphere still gives us trouble with radio waves, but it's kind of the best that we've got. So this decision to use radio waves was not driven by, economics or engineering. It was just driven by physics, and just that's the natural world we live in. So the spectrum of radio frequencies has been divided into bands. So we will discuss the IEEE radar frequency standard. So here comes a big old data table. So first we have high frequency, HF, which is 3 to 30 megahertz, followed by very high frequency. And you might be thinking, we don't have a lot of room to go from here. We're already at very high frequency and we're at the start of the data table. So they had to start getting clever with their names. This is from 30 to 300 megahertz. Next is, what else? Ultra high frequency, or UHF, which is 300 megahertz to 1 gigahertz. Next is L band, which is typically used by GPS satellites. So L band is 1 to 2 gigahertz. And that's followed by S band, which tends to be used by TDRS satellites. And that ought to sound a little bit familiar. We've talked about TDRS satellites in homework 1. TDRS satellites use the 2 to 4 gigahertz band for communication. Next is C band, which is 4 to 8 gigahertz. And if you're looking for a pattern in the letters on the left-hand side, you can stop looking because you won't find one. After C band is X band, which is used by the Deep Space Network, which we will talk about today. And that is 8 to 12 gigahertz. After that is the KU band, which is 12 to 18 gigahertz, followed by K band, which is 18 to 27 gigahertz. And then we have KA band, which is also used by the Deep Space Network, which is 27 to 40 gigahertz. Finally, oh, here we go. We have V band, which is 40 to 75 gigahertz. These are a little bit less used. And then the end of this table is W band, which is 75 to 110 gigahertz. So the reason I tell you this is just, and I'm going to clean up some of these because apparently I can't draw the letter 8 without getting in trouble here. There we go. And let's clean this up too. There we are. So the exact frequency ranges, I mean, this, this is not going to be on a test, just for your awareness that there are different bands of communications frequencies. Different satellites or different communication systems tend to favor certain bands over others just because of how they were defined. So, you might say, you might read some paper that the vehicle uses X-band communication with Earth to maintain its position estimate, that sort of thing. Well, that's okay. So now we know it's using the Deep Space Network, that sort of thing. Or I was in a meeting one time asking about how we do relative navigation between Artemis or the Orion vehicle and then whatever it's docking to, whether that's HLS or Gateway or what have you. And somebody in a not a rude but in kind of a dismissive way was just like, oh, we just use S-band comm for range. And like I knew what that meant because I had taken this class and seen this chart. So uses S-band communication. You can get your two-way range from that using some of the techniques that we'll talk about today. So there are two fundamental classes of radio wave measurements. And these are time-based So uses signal time of flight to estimate range. And I've already thrown some of that at you because that was in homework 2, problem 1, right? We were talking about how all we're doing is measuring the change in time that it took from the, the sender to the receiver. That change in time multiplied by the speed of light gives us our distance, right? That's sort of the idea there. So using time of flight to give us range, or is it, sorry, that's divided by the speed of light. I always get those mixed up. The distance is equal to rate over time. Rate, I did it again. Distance equals rate times time. I promise if you gave me a sec to write it out, I'd get it correct. Next is frequency based. And that uses Doppler frequency shift. To estimate what you might call radial velocity, or velocity along the direction, along the line of sight direction. This is sometimes referred to as range rate. There we are. So time-based and frequency-based. Those are the two types of measurements that we're going to be discussing today. So the first kind of general method of navigating using radio wave measurements is called time of flight or time of arrival. Time of flight, which is sometimes abbreviated as TOF, or time of arrival, which is TOA. Same idea, it's two different names. So the idea here is we estimate the distance between the transmitter and the receiver by measuring the light time between them, which is kind of what I said before. Just wanted to formalize that. Estimate distance from transmitter to receiver by measuring the light time between them. So estimating position using only range measurements is called trilateration. And this is fundamentally how GPS works. I feel like the layperson who's not educated in spacecraft navigation, everybody has at least a rough idea of what's going on with GPS, right? We know there's satellites overhead. We know we're getting information from the satellites. We know that your phone can process that information to tell you where you are on the surface of the Earth to within like startling accuracy, which is fantastic. And a lot of people worked really, really hard to reach that point. So definitely GPS is something pretty cool that we'll be talking about today. And I mean, it's at the point where navigation on the surface of the Earth is pretty much a solved problem. Like it's just use GPS. You know, we teach sailors how to use sextants the old-fashioned way to determine their, angle of the star or the sun or the moon off the horizon. But we do that as a backup in case GPS doesn't work. GPS is definitely the thing on the surface of the Earth, which it's difficult to overstate how fantastic and what a triumph that is. It's like GPS is phenomenal. And so we will be talking about GPS today. And so just a quick idea of what's going on here. If you've got some transmitter here, and you've got some transmitter here, and you've got some transmitter over here, and you know that you are this distance away from your first transmitter, and so we'll call this R1. and you know that you are this distance away from your second transmitter. Pretend that's a straight line or a perfect circle. We'll call this R2. And then similarly, if we know that you are this distance away from your third transmitter, and we'll call this R3, so maybe this kind of traces out an arc like this, then the intersection of those three arcs is where you, the observer, must be, essentially. So one of my pet peeves is when people use the word triangulation. They go, oh, we know I don't know, you see this in like crime shows. It's like, we know the strength of the cell phone signal from three different observers. That means we can triangulate their positions. Like, no, that means you can trilaterate their position, right? A triangle is three angles. A trilateral has three sides, three side lengths. It matters in that it's a completely different algorithm that requires completely different inputs. Ultimately still trying to answer the same question, trying to find position in 3D space or in 2D space. The problem scales to different dimensions. But it's a pet peeve of mine. Don't say triangulation when you mean trilateration. All right. Next point is we also use what's called time difference of arrival, or TDOA. So time difference of arrival, or TDOA. There we go. I'm going to try a little bit harder with that underline. That's slightly better. And so the difference here is, instead of actually measuring the absolute time, you're measuring the difference in time from two known transmitters. So we use the difference between time of arrival of signals from different stations. And those could be in space or on the ground, to estimate position. This is sometimes referred to as hyperbolic positioning. The idea there is that the pairs of stations, since pairs of ground stations are just pairs of stations, produce hyperbolic curves. So produce that can be a little bit weird to think about. We'll draw some pictures for that. This is, well, I think that's probably enough for now. So if you have this is a simple 2D case here, but if you're doing time of flight, if you're doing trilateration, right, you know that you're some distance away from this point and you're some distance away from this point. That basically gives you a Venn diagram shape, and there are two valid solutions. You've got one above and one below, and you need a third one to say, okay, well, now the intersection of three circles is a point. Now, in general, the three circles won't perfectly intersect, and it's going to be like a least squares problem to find the best possible solution that minimizes the distance error to either 3 points. But that's the general idea behind this. If you have two ground stations and you're looking at the time difference of arrival, then instead of intersections of Venn diagrams, you end up with these lines, which we'll show here in a second, which are lines of constant position. So let's say that you've got a baseline between two ground stations. If you were anywhere on this line right here, you would record a certain measurement, and it would be the same measurement, the same TDOA measurement would be valid for everybody on this dotted line. Similarly, if you were on this dotted line or on this dotted line, and it starts to look like a basketball, right? These, what I'm drawing, are hyperbolic surfaces, kind of more or less aggressive hyperbolas, right? And these are lines of constant position. So if you were here, or if you were here, or if you were here, or if you were here, you would get the same TDOA measurement. So these are lines of constant measurement. And we're not going to go into a ton of detail on TDOA, just for your awareness that there's an entire other way of solving problems like this. We're mostly going to be focusing on time of flight in this class, but TDOA is also neat. There's also something which you should be aware of called very large baseline interferometry. Or VLBI. This has been around for a little while now, and I think this is pretty neat. So the idea here is you can compare a signal from a distant object. Let's say you've got something all the way out at the moon or even further away, right? You receive that at two different ground stations on the surface of the Earth. And the change in time, between, assuming you've got all your clocks synchronized, the change in time between when you receive the signal at one time or another, at one station or another, I should say, actually gives you information about not the distance, but the direction too. So that the change in time, the whole system kind of works like an interferometer, and it gives you information about the direction of the incoming signal. So we'll draw a picture for that in a second, because I know that can be a little bit weird to wrap your head around. So we compare the same signal from a distant object as received by two ground stations. I guess two or more ground stations. Separated by a very large baseline. That's where we get the VLB part. And this is done to determine direction. And you might be wondering, just how large is the large in VLBI? So let me draw you a little diagram here. So here's the Earth, and say we've got a ground station right there, and let's say you've got another ground station right there, and let's say that you've got a spacecraft all the way out here. Well, so what's going to happen is the spacecraft's going to blast out a signal. And as those wave fronts get further and further apart, they start to become almost parallel. And you reach the point where incoming light waves are basically parallel. Now, we have a word for this in the navigation community, or really in the optics community. This is called collimated. If you've got light from a point source, or any other signal from a point source, by the time the wave fronts get large enough, they just start to look like parallel waves hitting you, and the object might as well be infinitely far away at that point. So starlight, when it approaches Earth, is collimated, right? We have no information about you can ascertain information about the star from the starlight, but in general, the waves of light are collimated. They look the same if you shift a little bit left and right, is essentially the idea that we're getting across. And so when that signal, it's going to eventually reach this detector, and then later it's going to reach this detector. And so we have a baseline between the two detectors, which gives us some information about the angle between the detectors and the original source of the signal. So there's my best diagram for VLBI. So when I say how large is the baseline, it's usually a significant fraction of the size of the Earth. We use stations that are separated across the planet, essentially, to accomplish this. So this is typically done with stations separated by a significant fraction of the Earth's circumference. And so you can ultimately determine direction from time difference. There we go. So VLBI is a tool that we can use to give us direction. We have TDOA. Now there are other things as well. We haven't even mentioned like frequency difference of arrival or frequency ratio of arrival. There's a lot of cool stuff that you can do with radar. What we're going to be focusing on this class. Do you need a third ground station? Yes, very good question, Corey. You do. Yep. So VLBI is a little bit like an interferometer, right? We get information about the signal in one direction from this. And so we would need a third ground station. I just was, this is a 2D example. So in 2D, 2 would be enough. In 3D, 3 would be enough. I like that question. So in this class, we'll be focusing on getting distance, Doppler, and sometimes line of sight directions to things. And that's really what we're going to be focusing on in this unit is distance, Doppler, and line of sight, which distance, Doppler, and line of sight, distance is range, Doppler is range rate, and line of sight is also called bearing. So R3B, those are kind of the class of measurements that we're going to be focusing on when we talk about the Deep Space Network or about GPS. GPS is pretty much exclusively range measurements. But yeah, there's a lot of cool navigation that you can do with R3B measurements. So why don't we go through an example? So an example radio frequency system is GPS. And that's one that pretty much everybody has at least interacted with at some point before. So the United States, anybody know what GPS stands for? Oh, I think I'm starting to lose people, or you're feeling a little bit tired.
Global positioning system.
Good. Yep. United States Global Positioning System, which is not the only game in town, but it is one of them. GPS is one example and the first of a number of global navigation satellite systems. So sometimes you'll see, instead of GPS, you'll see GNSS, which is the more generic umbrella term. GNSS, Global Navigation Satellite Systems. So there are others. GPS is not the only game in town. So Russia has one. Makes sense. They're the other big spacefaring country. Now we have China as well. Russia has something called GLONASS or GLONASS. I've only read it, so I don't know how you're meant to pronounce it. I also can't remember if it's one or two S's. I think it's two S's. The European Union has something called Galileo. And China, kind of up-and-coming spacefaring country, which has done quite a bit in recent times, has something called Beidou, which accomplishes same idea. And it makes sense. I mean, America could just flip a light switch and turn off the GPS signal to different countries, or we could scramble or encrypt it. Right now, GPS is free to use, I think, everywhere. I think it's limited in some places. Originally, when GPS was made available to the public, there were limitations on the accuracy that were kind of imposed on GPS. So GPS is actually quite a bit better for the military than it is for just average people. But I believe those have been removed or at least relaxed, because it used to be that GPS was originally released to the public for aircraft navigation to make sure that we didn't accidentally wander into enemy airspace, because there were some incidents where that happened. And it used to be good to within, maybe 100 meters or even 50 meters. But nowadays, like your GPS can tell what room in your apartment you're in, right? So it's gotten pretty extreme in how accurate it is. So GPS performs navigation by trilateration. Performs navigation. We've really been hammering that home today. By trilateration. and consists of 3 segments. There's 3 parts that make GPS tick. So the first is the space segment. So there are 24 satellites in the baseline configuration. And they are launching more GPS satellites all the time because old ones obsolesce. So there's more than 24 up there now. GPS satellites are in near circular 12-hour orbits. So GPS satellites are in near circular 12-hour orbits. So their radius is approximately equal to 26,560 kilometers. They have a 55-degree inclination. And so you can imagine that this would be fine. That would be absolutely no issue for anybody living below 55 degrees latitude, which is most of the United States, I think, except for Alaska. But when you get towards the Earth's poles, you start to be able to observe fewer and fewer GPS satellites, and you can actually start to have some problems. So you might have seen footage. I thought this was pretty cool. I saw footage of an airplane flying over the North Pole of the Earth, and the GPS just goes completely haywire because it doesn't know what to do. And also, I said, well, why don't we just use our compass? Compasses also don't work at the North Pole because it just points you to the North Pole. And the closer you get to the Earth's magnetic poles, the more the behavior gets to be a little bit erratic. And so, yeah, navigation around the poles of the Earth is something that we don't exactly have figured out yet. But it's also, most people live closer to the equator. So kind of struggles near the poles. There we go. Let's see. That 12-hour period, 12-hour orbital period, produces repeating ground tracks. So you can imagine that how do we put it here? If you have the Earth and then you've got something orbiting the Earth, now it kind of looks like Saturn's ring, and you were to take the ground track and of the point directly below the spacecraft at any given point and plot that on a map of the Earth, it generally produces a sine curve, repeating sine curve. Or depending on the nature of the orbit, it might not be a repeating sine curve. It might be that as you continue to plot it, it never quite loops back in on itself. So the International Space Station's ground track is always kind of clipping back every orbit because you can imagine that the Earth rotates underneath it as it's doing its orbit. But for a 12-hour orbit or a 24-hour orbit, you've got to have a kind of repeating ground track, which is nice. It makes things a little bit simpler if you're trying to think about, well, which parts of the Earth can see this spacecraft. It's a little bit easier. And then let's see. Oh, the last bit, there are 6 evenly spaced orbital planes with 4 satellites each. So you can imagine each plane is a 55-degree inclination. They're separated by about 60 degrees. And then each one of those has 4 satellites, which are each separated by about 90 degrees. And that's the kind of swarm of satellites that there are over the Earth right now for GPS. And yeah, at any given time, you can see typically 4 or more of those, which is great because that's the minimum number to solve for your position. So that's the GPS space segment. Let's get on to the GPS control segment. There we are. So the control segment has a or a master control station, or MCS, which is near Colorado Springs. Can't speak today, sorry. Colorado Springs. And that operates the satellites. Providing command and control, etc. There is a constant need, and this is something that I think a lot of people tend not to think about. When you're doing your GPS-based position estimation, your uncertainty in where you are cascades from any uncertainty that there is in where the spacecraft is. So we need to have unbelievably high accuracy knowledge of where every GPS spacecraft is all the time to within a nanosecond, right? Because we need to know exactly where it was when it sent the signal that you're receiving, because you're receiving the signal that was sent a while ago, right? That's the way that the radio transmission works. And so because of that, we need unbelievably high accuracy orbit determination. And so there is essentially just a bank of supercomputers running around the clock, making sure that we know exactly where all the spacecraft are. So there is a constant need for not initial orbit determination, but precise orbit determination. So not treating the Earth as a point mass anymore, and also considering n-body gravitational effects. The works, right? This is the Cadillac of orbit determination, and there are dedicated supercomputers to accomplishing this. There's also a global distribution of US Air Force, and this is where it might now be US Space Force. I'm going to guess that it probably is. So my notes are from before the United States Space Force was formed, or very shortly after. But these are monitoring stations. I'm going to guess that their operation was transferred over to the new branch. And so those monitoring stations are what we use to take measurements of the GPS satellites. And then the precise orbit determination is done on the data that come from those monitoring stations. And finally, there's the segment that y'all are most familiar with, which is the user segment. This is like the PBS part where it says, and viewers like you, thank you. So this is static and mobile GPS receivers. Well, what do? They receive and decode GPS signals and perform trilateration. So at the moment, we might not be comfortable doing trilateration, but your phone is. So that's the other bit here. This includes your cell phone. And so you can imagine, this is just like a quick diagram, because we haven't had a diagram in a little while. But so imagine that you've got your Earth, and you've got somebody standing on the surface of the Earth, and you've got a satellite overhead. Pretend that's a rectangle. And you've got another satellite over here. And you've got another satellite over here. And originally I was going to draw orbit tracks for each of these, but I think it's going to get way too messy. And then you've got another satellite over here, and these are each orbiting the Earth at 12 hours essentially. And you have measurements to the individual from each of these. And the GPS satellites, they don't know where you are. They're just blasting out a signal in all directions. And your phone or whatever other device you have is listening for GPS signals in general. Ultimately, it gets several of them, and then it decodes them to say, oh, okay, well, that gives me information about how far away I am from this satellite, how far away I am from this satellite, so on and so forth. And that gives me enough information to perform trilateration. So we'll get into the math of trilateration maybe a tiny bit today, but mostly next class. And yeah, I think the next point I was going to make is another example RF system. But why don't we pause for a minute? Any questions on GPS operation, or anything else so far?
So is the signal that the GPS is sending out, does that have some amount of time data included, or is it like, I don't know, what does the signal sort of contain?
Yeah, it absolutely does. So you can imagine that the absolute bare bones information that you would need in the signal is, what time do I think it is? Because what happens is it sends the signal at whatever time it thinks that it is. You receive the signal at whatever time you think that it is. And so your measurement is delta t. That's kind of what we saw in homework 1. So I kind of threw that one to you already. But the change in time between the receiver and the observer is essentially your measurement. But there's actually a lot of other stuff going on under the hood, because it's your, how do I put this? Because the speed of light is so fast, the clock accuracy needs to be on the order of nanoseconds, essentially, to get really decent position estimation. And your phone's clock isn't that good. And actually, the GPS clock also isn't that good. You need very high accuracy. Uh, what are they? The clocks we talked about at the beginning of class. The atomic clocks. We need atomic clocks to keep very, very precise idea of what time it is. And so the GPS satellites are constantly being updated with what time it actually is, so that they know. And then there's relativistic effects you have to account for. It gets to be a bit of a mess, but the core of the message is, okay, here's my name, here's which satellite I am, here's where I think I am right now, and here's what time I think it is. And that information is enough that you can actually decode where you are. There's a lot of other information about what's included in the actual signal that I've opted not to go into just to save time. But if you're curious and you want to read more about it, first of all, there's entire textbooks on how GPS works. It gets pretty complicated. But in the course notes that I posted from when Dr. Christian taught an equivalent course, he went into a lot more detail on GPS than we're going to in this class. And so there's always more you can read about. But yeah, that's a good question. The core of it is, here's what time I think it is. But yeah, it gets pretty complicated. Other GPS discussion points? All right, cool. So I know we've been going for a while. Actually, we've been going for an hour and 45 minutes, if you think about it. So why don't we take another 5-minute break? I'm about halfway through my notes for today, and we can come back and keep going. And of course, if y'all need to leave, if you have other stuff going on, you're absolutely dismissed. But we're going to keep this train rolling for now. So it's 6:43 for me, 7:43 for you. So let's come back at 7:40. Well, it's like a stale 6:43. Let's call that 7:49. That's when we'll come back.
I've got another quick question. If
Sure.
you've got a second.
Yeah, go for
So
it.
how precise does your phone's internal clock have to be to get this to work?
So your phone's internal clock needs to know what time it is. You know what? That's a good question. I got to think about that for a little bit. So your phone knows what time it is from the internet. Would GPS work if the internet wasn't there? Well, it's like, well, you'd start to get some errors propagating. Yeah. I'm not exactly sure is the short answer to that question. I do know that clock accuracy, and we're going to talk a lot about in the next lecture or two about clock bias. If your clock is running slow or running fast by a tiny, tiny fraction of a second, that can throw off your position estimate by tens of meters, right? So the exact accuracy is tough to say, but I know that your phone has a decent clock, but it certainly needs to be, it needs to be augmented in some way. It needs to get that information from outside sources, essentially.
Yeah, that's interesting because I have a little independent GPS thing that will only ever occasionally connect to the internet if you have it like in your house and you've like given it the password and it's off most of the time. So does is it possible that the device figures out the time from the satellite signal it's receiving?
Yeah, that's what I'm wondering too. I'm not exactly sure because the what you can't know is the time of flight of the light and what time it actually is kind of at the same time. You need to pick one, right? There are like bidirectional and tridirectional ways of doing radiometric ranging to kind of get rid of the need for the receiver to have a very accurate clock. But yeah, I'm not exactly sure. I think what the big issue is really not as much the clock precision, because I mean the clock on your phone is it is counting nanoseconds as it's going. It's more the clock accuracy, and in this case the clock bias, right? The change in time between your device and the spacecraft, and you do ultimately end up estimating your clock bias as a state. That is one of the things that comes out of it. So I think some of the inaccuracy in your clock is essentially estimated instead of fed into the equations as an unknown, and that rescues you from some of the error. But yeah, no, this is GPS is a little bit out of my depth, so it's not that hard to ask me a question that I don't know the answer to. So that is a good one, and that's cool that you have like a GPS thing running like on your own. That's awesome.
Yeah, thanks.
Mhm. Hey Merritt, I don't know if you're there. I see you have a hand up. Is that stale or
Oh,
is
that
that
was that was excellent.
okay? No problem. All right, welcome back. Figure we'll get back into it now. Let's see here. All right. So we talked about GPS just at a conceptual level. There's still a lot of open questions about, the math of how GPS is accomplished. And uh, GPS deserves its own course, not just its own lecture. But yeah, that's kind of the depth that we can go into today. Next, we're going to talk about something else which deserves its own course, not just its own lecture or, partial lecture, which is the DSN, which I think is at least as cool as GPS. So DSN stands for the Deep Space Network. The Deep Space Network is the most sensitive telecommunications system in the world. And I think about that and it's like, well, it's not technically in the world, right? Or out of the world. So it is operated for NASA by Caltech's Jet Propulsion Laboratory. I spell that right? Yeah. Or JPL. It was first established in 1958, which for all you history buffs out there, was also the year that NASA was first established. So this has been around for a little while. And it is the primary means of communication with interplanetary spacecraft. Communication and radiometric navigation. The DSN consists of 3 deep space communications complexes, where the abbreviation for that is a DSCC, right? Deep Space Communications Complexes. So there are basically 3 DSN stations in the world. We only need 3, which is weird, but I'm going to draw a picture. The first is in America. It is in Goldstone, California, which is in the Mojave Desert. That is the one that JPL considers to be in their backyard. The next one is near Madrid in Spain. And the third one is Canberra, Australia. You might be thinking, gosh, those are completely weird and random places to put ground stations. Actually, somebody thought this through. Because imagine you have a situation like this, where, again, here's the Earth. If we want full sky coverage, what would be great is, and maybe I'll even color code this. Yeah, let's do red. So what would be great is if we have a red ground station which provides coverage to everything that it can see. And then if we had, we'll do a blue ground station, and this blue ground station provides coverage to everything that it can see. And then let's say we had a green ground station. You're starting to see where I going with this. So you had a green ground station, and it provides coverage to everything that it can see. Then we have these 3 blind spots, which are relatively close to the Earth, but then everything else can see at least 1 ground station, and there are some areas that can see 2 ground stations. So if you're really smart about how you place your ground stations, and it's roughly something like 120 degrees apart, that gives us the best possible coverage of deep space. So these were chosen very strategically. 120 degrees. It's not exactly, but you get the idea. 120 degrees. Gives us the best possible coverage of outer space. Each complex has several antennae. So there's usually an 11-meter dish. There's usually a 26-meter dish. There's usually several 34-meter dishes. And there's usually one big kahuna 70-meter dish. which is like approaching the size of a football field, right? Absolutely humongous. Oh, I should mention a couple of notes here on this diagram here. The blind spots are all close to the Earth. And there is essentially continuous coverage. In deep space. There we are. So that gives us some information about what's going on the ground. Now there's also, those are the observation stations. There's also a, let's see here. There is a centralized signal processing center. Where else? At JPL. And what it does there is it remotely controls an antennae, specifically the 34-meter and 70-meter dishes. It generates and receives, or sorry, one thing at a time. It does receive, but that's the next bullet point. Generates and transmits spacecraft commands. And also receives and processes spacecraft telemetry. So actually, we talked a little bit about this during the live stream today when we were learning about the communication that they were doing with the Nova C lander, the Odysseus lander. You might have, I think they mentioned, almost certain that they mentioned Canberra, Australia, and using the Deep Space Network to try to contact it. If they didn't mention that, then maybe I'm going nuts, but I'm almost certain they said that in the live stream at some point. So this is definitely something that is still used today. Modern spacecraft didn't always work this way. Modern spacecraft communicate with the DSN on X-band and Ka band. And so DSN does not just use range measurements, it uses range and Doppler measurements. So that's essentially range and range rate. It also has a technique which is called delta DOR, which is delta, you might read about this in your journeys through academia, delta differential one-way ranging. Which is a form of very large baseline interferometry, which means we have baryon measurements as well from the Deep Space Network. So that tells us that we get our 3B measurements. All right, so there are 3 cases. I'll kind of make myself a little room to write here. Let me know if I need to zoom back up again. So there's 3 cases that are worth discussing within the Deep Space Network. So the first is one-way ranging, which is near Earth. The second is two-way ranging, which is Jupiter and beyond. And the third is three-way ranging. Which is Pluto and beyond. And you might be saying to yourself, gosh, we can communicate with things at Pluto. It's like, yeah, we can communicate way past Pluto. It's like we're still in communication with the Voyager spacecraft, which are like arguably outside the solar system, depending on where you define the edge of the solar system. So yeah, we can communicate quite a bit past Pluto. Near Earth, and get ready, because here's Paul's best attempt at some art. Say this is the Earth. And I'm actually going to draw the same diagram 3 times here. There we go. And let's do my best little ground station here. That's okay. It gets the idea across. Maybe I'll try to close that up a little bit. And then do the same diagram here. And then similarly, there we go. So if you're near the Earth, it's just a one-way discussion. Nice and simple, right? You've got your spacecraft, and it's just, boom, there we are. You just tell it what to do. All right. The problem is one-way ranging, there is no way to remove spacecraft clock bias, which is a bit of a problem. Two-way ranging, what we do is we send a signal to the spacecraft, and by the time something is out to Jupiter, it's going to take minutes to hours to actually get a return signal, depending on where the configuration of the planets are. And so in that case, what we'd want to do is we would calibrate what we would call the turnaround time. So we would send a signal to the spacecraft and say, respond immediately when you get this. And then we know, okay, we sent the signal, we received the signal back. We get enough information from the turnaround time. So the spacecraft echoes the signal back to us. And that gives us enough information to remove clock bias. So you might hear about DSN one-way ranging, DSN two-way ranging, or even DSN three-way ranging. Three-way ranging is more useful when you get out to Pluto and beyond. So this would be something where we receive something from the spacecraft, we have communication between 2 ground stations, and in this case, we do this because signal takes hours to days. So we don't have time to kind of have a rapid back and forth trying to perform navigation. We try to bounce the signal around as much as possible, so we don't need to wait for the next signal, or we don't need to try to minimize the bandwidth of communication that we need with a spacecraft, simply because the time it takes is so crazy long. But so just for your awareness, there's one-way ranging, two-way ranging, and three-way ranging with the Deep Space Network. We're not going to be going into a ton of detail on that. We're going to be focusing more on what we do with the measurements when we get them. And actually, what I thought we would do next, unless we have any questions, is go into kind of a toy problem of trilateration. So this is a trilateration, just because I wanted there to be some math today. We're going to do a lot more math on trilateration next class. So I wanted us to think through, as navigators, how we would solve a trilateration problem, but I want to make abundantly clear in the red text, this is not what is actually done. This is closer to a thought experiment or just an example, right? We'll actually go into a little bit more detail on what's actually done next class. So our trilateration toy problem looks a little bit like this. Let's say we've got a world frame. And let's say we've got some ground station here. And you can imagine it as an observer in space with a ground station that's transmitting, Or we could say that we've got a, let's do it this way. We've got a satellite. And in this case, we have one satellite over here. Maybe we've got another satellite over here. And so we're going to call this vector pi for just some point, right? Whereas over here is your observer, like a little person. That's meant to look like a person. Let's try that again. People have torsos, right? That's a little bit better. And so you've got this signal that's being transmitted from the spacecraft down to the person, and you've got, you know, maybe some other, we'll leave this one out for now. Yeah, that's complicated enough already. And so, okay, the question is, right, let's say we have, oh, we should mention that the distance from the transmitter pi to the receiver at r, we're going to call that rho I. We have several range measurements, rho I. How many is enough? And so that's an open question. It's not a rhetorical question. How many range measurements do we need to nail down somebody's position in 3D space? So we can think about it this way. A range measurement is 1 degree of freedom. And I'm going to rewrite this question as how many is enough to estimate position? Well, your position in general is 3 degrees of freedom, is it not? And so that would imply that we need, this might have been what you were thinking, we need 3 measurements give us a solution, but it's not quite that simple. 3 measurements give us a solution. 4 or more measurements give us a unique solution. What do I mean by that? So imagine you've got an observer. Let's say you've got some station here, and you know that you are this distance away from it, and pretend that's a perfect circle, right? And let's say you've got some other here, and you're basically creating a Venn diagram. Hang on, a Venn diagram. There we go. And your question is, where is the observer? You know that you're this distance away, you know, R1 away, maybe we'll call this rho 1 away from some position P1, and you're some distance rho 2 away from position P2. In 2 dimensions, just having 2 measurements still gives you 2 possible solutions, doesn't it? So what you really need is a third station, and you say, oh, I'm also rho 3 away from P3, and when you draw that circle, now it's clear to you that there's only one solution. So generally you need n plus 1 measurements, where n is the number of dimensions of the problem that you're working with. So I'm gonna erase that. That is not my best artwork, just wanted to get the idea across. In general, you need n plus 1. If we were in 4th dimensional space, we would need 5. And of course, if we have many, many extra measurements, that's totally fine, because it ultimately turns into a least squares problem. And least squares problems don't mind extra measurements. So just to make it clear here, rho I is the vector r minus the vector pi. So it's the vector between them, but then it is that distance. So it is normalized. So here's a challenge. And I realize that we're going pretty late. Y'all are hanging on by a thread. I want to give us about 5 minutes to attempt this. And then folks who are watching later can try to attempt this as well. So we're going to give it 5 minutes. So right now it's 8:09. We're going to go until 8:14. Challenge is to use this equation to build a linear measurement model for R that looks like y equals hx. That's what we're going to try to accomplish. I'm going to pause for about 5 minutes and let people just chew on that for a little bit, see what you can do with that equation. And yeah, we'll see what we can do. This is a little bit similar to what we had in homework 2, problem 2. I'm just curious what people would come up with if you could measure your ranges. All right, that's enough suspense. We can go through the example here. I'm curious, did anybody take it all the way to ground? Do you think we have an actual solution, or was this kind of a exercise in creativity? No, maybe not. Sounds like this was an exercise that, was good, but might have resulted in some wheel spinning. Let me show you how I would go about solving this. So first, let's say we have rho I, that's equal to the norm of r minus pi. Well, so the norm of r minus pi could also be written as r minus pi as a vector transposed with r minus pi. And then all of that, because this is now a scalar value, to the 1/2 power, or the square root, essentially. Right? So if you take r minus pi as a vector, transpose it with itself, that gives you whatever that distance is squared, square root, it gives you your range. So all I did was rewrite this equation. But this just begs, like, why don't we square both sides? It's like, okay, let's see where that goes. rho I squared is equal to R minus PI transpose R minus PI. And this just kind of reminds me of like high school when we had to FOIL things or, kind of distribute. So in this case, if we have a vector minus a vector transposed with a vector minus a vector, we can actually do a little bit of distribution. So rho I squared would look like what? Well, it would look like R transpose R, that's first. Outer and inner are really just minus 2 PI transpose R. And then last would be plus PI transpose PI. Okay, so first I'm going to just make a couple definitions. If little r is equal to the norm of the vector r, maybe and then PI without the hat is just the norm of the vector PI with the hat, then we can kind of do an extra step here. So this is really saying, okay, rho I squared is equal to R transpose R is just R squared, right? That's the vector R transpose with itself. This is still going to be minus 2 PI transpose R. And then PI transpose PI is just going to be PI squared. Okay, great. So now I want to move some things over to the other side of the equal sign. I'm going to write this as rho I squared minus PI squared is equal to R squared minus 2 PI transpose R. And now we have basically won. We've pretty much accomplished it because now we could think of it as being rho I squared minus PI squared is equal to 1 negative 2 PI transpose R squared and then the vector R. So this is a 4x1, which we'll call X. This is a 1x4, which is one element of the matrix H. And then this is a 1x1 scalar term. But ultimately, we could scale this up to get something that looks like Y is equal to HX. And we can solve in the least square sense for R, which is kind of what we care about, and then this other R squared term that we don't care about as much, which, I mean, it's kind of redundant information, essentially. But that is a trilateration toy problem. So I'll make a note here. This is a 4 equations, 4 unknowns. So 4 equations, 4 unknowns. Solve using least squares. Or you could use maximum likelihood estimation if you had different uncertainties in each of your ranges, right? But so this is just, I wanted to go through the exercise of starting with a measurement model like this, which is kind of just comes straight from physics, it comes straight from geometry, and then take that all the way to a linear system of equations that we can try to solve for our state, right? So that's one of the things that we're going to be covering again and again in this class. We did a little bit of on homework 2. It's also going to come up on homework 3. But so I want to be abundantly clear, this is a great exercise on how to go from this equation to this linear system, but this is a simplified form. This is not what is actually done. It's a little bit more complicated in space. And actually, we're going to talk about that right now. So today, I have 1 page of notes left. It's going to take us about 10 to 15 minutes, and then we'll be all done. We're going to set up the problem of radiometric ranging, and then next class is going to be all math, solving the problem of radiometric ranging, solving the trilateration problem using 2 different very fancy methods, which are essentially beefed up versions of least squares problems. And then the other would be, we're going to be spending some time on triangulation using line of sight measurements. So that's going to be the rest of the next 2 lectures. So this next topic is called radiometric ranging. There we go. So let's be a little bit more specific about this. Suppose we wish to use light time of flight to estimate the distance between points in space. So kind of the big question, the big red flag about the last example we did was, well, Paul, where does this range come from? We don't measure range. We get GPS signals. GPS signals don't have range baked into them. We have to estimate range. Maybe you were thinking that. And that is part of the problem. So we're going to talk about that right now. So for the rest of this analysis, I'm going to define the position of the receiving antenna is going to be, it's going to be R sub R, which changes with time. Then there's going to be propagation. This is the actual length of time the signal was in space, going from one signal, going from the transmitter to the receiver. And then there was the position of the transmitting antenna. Which is going to look like position of the transmitter, which is itself a function of t minus tau, right? Because you don't know where the transmitter is, you know where the transmitter was tau seconds ago. So this is at the time the signal was sent. And then we have to consider that there are biases in both clocks. And that causes measured time to differ from real time. So here comes one of my favorite equations in this class, and that's the equation for transmitter time. So the time at the transmitter, which is itself a function of time, is equal to time plus delta t t t. Like, hey, dog, I heard you like the letter T, so I put some more letter T's in your equation. So the transmitter time, which is a function of time, is the actual time plus this delta transmitter time, which is also a function of time, and that's the bias term. And it's going to make a little bit more sense when we talk about receiver time, maybe, I hope so. The receiver time, so time at the receiver, which is a function of the true time, is the true time plus delta TR of T. And so we can think of this as the bias, and this is the true time. Okay, so continue to bear with me. We're building a measurement model. We're trying to set up a problem in the next couple of lines of math that we're going to then attempt to solve next class. So the difference between the measured transmit time and the receive time gives us something called our pseudo range. So the difference between the measured transmit time, so we don't know the true range. We know the difference between the measured transmission time and receive time is used to obtain a pseudo range. So we don't know the range, but this is our best guess based on what we've seen. So we actually have to estimate rho before we even get to the point of being able to plug rho into a linear system of equations. So that's going to look like this. Okay. Rho, our pseudo range, which is a function of time. So I want to be abundantly clear. This is pseudo range. Okay. So pseudo range is the speed of light times TR of T minus TT of T minus tau. Okay. Seems like a lot of T's and a lot of taus. All I'm saying is it is the transmitter time at the instant that the message was sent, which was tau seconds ago, And that is kind of the before picture. The after picture is the received time. So you've got the time at the receiver minus the time at the transmitter. And this tau is really the thing that we're after, right? The tau, we're going to try to isolate that tau if we can. That's the length of time the signal was in the air, which actually is the information about the distance. And then there's a bunch of other crap that we don't care about, but it is in there and we can't ignore it, right? Now, further, c is the speed of light. And you might be familiar with the idea that the speed of light in a vacuum is constant. That's great. Radio signals from GPS satellites are not traveling through a vacuum. First of all, space itself is not a perfect vacuum, right? There's still the interplanetary medium. There's even the interstellar medium. You know, you'll never find a true vacuum wherever you go, right? And then there's the fact that then it has to travel through the Earth's ionosphere, and then it has to travel through the Earth's troposphere. So the speed of light is not as simple as you might think. That's an additional source of headache for us here. So let's expand this a little bit, right? Rho of t is equal to c and then in parentheses. Okay, so what we're going to do is the transmitter time and the receiver time, we're going to make some substitutions here. So we have t plus delta tr of t. So true time plus the receiver bias minus, and then in parentheses, true time plus transmitter bias, and then minus tau. There we go. That's the whole thing. All right, now we can start to simplify a few things. So for example, time is going to cancel out with time. So our pseudo range is going to look like rho is c, and then this is delta tr of t minus delta tt of t minus tau, and then if we distribute, this is now plus tau. Okay, great. So here's what we're going to do. We're going to kind of clean this up one more step. Rho of t is equal to c tau, so I'm going to separate that out, plus c, and then in parentheses, delta tr of t minus delta tt of t minus tau. Right? So this is the interesting bit. That's what we're after. And then this, everything over here, is going to be some function of clock biases. Okay, stay with me. Stay with me. So this interesting bit, let's rewrite this one more time. Rho of t, c times delta t is the actual distance, right? So we get the distance between, or it's approximately equal to, r of t minus rt of t. So that's the actual like range that we're interested in. That's what we're after. Oh, you know what? I made a blunder. Apologies. Get your erasers out, everybody. The left-hand side of the equation is c tau. Okay. So c tau, the actual time that the light, the light-based signal or the radio signal is being transmitted, c tau consists of what we're after and then some other stuff. So remember how I mentioned, we got some other terms here. IPP of t plus IP of t plus TP of t. So remember I mentioned the speed of light is not as easy as we think. We also need to model tropospheric delay. Delay due to the Earth's troposphere. Ionospheric delay. Ionospheric due to the Earth's ionosphere. And then interplanetary medium delay. Whatever reason my brain wants to say display. Nope. Interplanetary medium delay. So in the previous course, when John Christian taught this, he decided to go into much greater depth on tropospheric, ionospheric, and interplanetary medium delays. I've decided to omit those in the interest of time and try to cover different things with that. So really, this would be an entire other lecture, at least, going into the different delay models and how we handle those, and then all the other things that we have to take into account. I'm going to try to simplify things. So I'm going to say in this class, we're going to ignore these, but you can't do that in real life. So if any of you go directly from this class to working in GPS, please remember that I said that it's not this simple, but we are going to try to cut a few things out. So finally, therefore, our pseudo-range measurement is what? Here we go, starting all the way on the left. Rho of t is equal to r of t minus rt of t. So that's the actual distance that we care about, plus c times delta t r of t minus delta tt of t minus tau, plus interplanetary medium delay, plus ionosphere delay, plus troposphere delay. Okay, here's the good news. In reality, we estimate these using models. And actually, to your question earlier, I forget who asked the question, but part of the GPS signal actually contains information about the most up-to-date ionospheric, tropospheric, and interplanetary medium models, because those have parameters in them that are changing as a function of time. And so, yeah, information about the delay effects is actually also baked into your GPS signal so that you can account for that after the fact. In this class, we will ignore, just so we have one less thing to worry about. Next, the transmitter bias is typically calibrated. That's your GPS clock bias. That is JPL's problem. That is not your cell phone's problem. We're going to handle the fact that it's your cell phone's problem. So we're going to simplify this, and we're going to put a little squiggle over it, not because it's necessarily noisy, although it will be noisy, but it's because we've chosen to just drop some things or estimate them away or take them into account in some way, shape, or form. So this gets a little bit simpler. We get r of t minus rt of t plus c delta tr of t. Okay. So our pseudo range measurement is the actual range between the transmitter and the receiver, the part that we're really interested in, plus this other term, which we are going to define as the letter b of t for receiver clock bias. Okay, so finally, and I really do mean finally, this is the last equation I'm going to write today. We're going to drop the of time notation just for brevity. Our equation looks like rho I, so the ith measurement, is equal to RR minus RTI, the norm of that, plus B, which looks an awful lot like what we had before. If we go up to our toy problem, range is equal to R, I used the letter P before, now we're using R sub T, but same idea. The problem is it's that clock bias, right? I made a note about that. In this toy problem, we ignore clock bias. That's a no-no. Now we're looking at the grown-up version of the problem, which has a B in there. And so you could think of it as really being, if we wanted to expand this, this is the same equation. I wasn't lying earlier. This is, there we go. RR minus RTI transpose, RR minus RTI, and then all of that to the 1/2 power plus B. So the question is, if we have something like this, where we've got our measurement or pseudo range measurement coming in from the spacecraft, which comes from the speed of light and the change of time, that is then equal to this plus our clock bias. And we're trying to take that and turn that into a linear system of equations that we can solve in the least square sense to estimate your position, essentially. So it's, we will see how to solve this for your receiver position next class. So this is to be continued. There we go. And that is pretty much all we're going to discuss today. We've gone plenty late already. So there we go. Good enough. To be continued. We'll talk about this next class. What we've covered today is setting up our radiometric range model. So this is the model of our physics, so that in the next class, we will set up and solve the estimation problem, which we will see we can't solve with least squares or weighted least squares or MLE. We actually need even more fancy estimation methods. The two that we're going to be talking about are iterative nonlinear least squares and Bancroft's method of solving a trilateration problem. And then we'll go into triangulation. And by this time on Monday, or hopefully earlier than this time on Monday, you should have enough information to attack homework 3 and do a fantastic job at it. So thank you very much for sticking around to the end. Y'all are extremely dedicated. You're free to go. Class is dismissed, but I will stick around and answer any questions that might have come up.